In this podcast, we're going to talk pretty in depth about ice tables. Ice tables are a tool that we will use to solve equilibrium problems. There are going to be three kinds of equilibrium problems that we're going to be dealing with. Ones where only the reactants are initially present, some where only the products are initially present, and then some equilibrium situations. All right, to solve for equilibrium concentration, you have to make an ice table. So we're going to just start with this reaction right here. We have H2O gas plus carbon monoxide gas is in equilibrium with H2 gas and carbon dioxide gas. The K of this reaction at some temperature is 2. Now, if we started with 8 molecules of H2O and 6 molecules of CO, how many molecules of H2O, CO, H2, and CO2 are going to be present at equilibrium? Well, in order to solve that, we have to use what's called an ice table. But before we can start using the ice table, it's best to go ahead and write the equilibrium expression for the problem. So we're going to go ahead and write our K. So we got H2 and CO2. These are all 1-to-1 ratios, so you don't have to put any power at the top. Okay, there's our equilibrium expression right there. All right, now we're going to jump into the actual ice table. ICE stands for initial concentration values, C stands for change, and E is the equilibrium. Okay, now I want you to notice that in this particular problem, we only have reactants initially present. So it said we started with 8 molecules of H2O and 6 molecules of CO, okay? So we have approximately an 8 molar and a 6 molar situation here, okay? And we had 0 H2 and CO2 to begin with. Now the change is dependent upon which way the equilibrium will shift. Well, we know in this case that we don't have any products made, so we know that we're going to have less reactants because that's all we're starting with. They have got to make some products for us to reach equilibrium. And we know over here that we are going to gain 1 mole of each of these substances because they start at 0. Now you combine the two boxes into the equilibrium box. We got 8 minus X, 6 minus X, X, and X. Okay, now we need to plug this into our equilibrium expression. Okay, so we had H2 and CO2, so there those are X and X. And then H2O was 8 minus X, and then CO was 6 minus X, okay? So we plug that all in, and we're going to go ahead and pop in the K value that we were given in the very beginning, okay? Now it's just a simple math problem, okay? So you got X times X, so that's X squared. All right, and down here, you're going to have to use FOIL. FOIL, hopefully you remember from math, but it's first, outside, inside, last. So you got 8 times 6, because those are the first. You got 48. All right, and then you got inside, so we have negative x times 6, and outside 8 times negative x, so that totals negative 14x. And then last, negative x times negative x is x squared. All right, now we're going to simplify this, so I'm going to go ahead and cross multiply this whole entire thing times the 2. Okay, so that's going to give me 96 minus 28x plus 2x squared is equal to x squared. All right, now I'm going to get everything on the same side of the equation, and I'm going to go ahead and reverse it so that I'm in the order of x squared, x, and just the number. So we have minus x squared, so we get x squared minus 28x plus 96 is equal to 0. Now we're at a point where we can use the quadratic formula to solve for this problem. All right, now the problem can be solved in terms of the quadratic formula. So we got negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, where the term in front of the x squared is a, and the term in front of x is b, and then the numerical term is c. Okay, so you can do all this math if you prefer, or I have a little simpler method that I like. So I'm going to use my quadratic formula program on my calculator just to save me some time. So my A was 1, my B term was negative 28, and my C term was 96. Okay, so it gives me two values. It gives me 4 and it gives me the value 24. So we need to evaluate both of those values to see which one makes the most sense. Okay, so looking at the equilibrium, oh snap, my thing done went flying through, didn't it? Hold on. Okay, there we go. Right slide now. Okay, so when you're looking at, we had 4 or 24. 24 really didn't make any sense because 8 minus 24 or 6 minus 24 would have gave us negative concentration values on our reactants. And negative concentration values are not possible. So 4 had to be the correct number. Then you want to go plug X back in to everywhere that we were able to solve. To get the actual. So we got 8 minus 4 is 4, so our concentration of H2O at equilibrium is 4. Concentration of CO is 6 minus 4, which is 2. And then H2 and CO2 both were just X, so they're just 4. Okay, so to do a little recap on all those steps, there were 4 steps to determining the equilibrium concentrations using the ICE table. First, you write the equilibrium expression. Second, use the ICE table beginning with the initial concentrations. Plug in your equilibrium concentrations into the equilibrium expression and solve for X. And then substitute X into the equilibrium concentrations to find the actual concentrations. All right, so now let's do the same procedure, but we're going to have the second type of problem. In this problem, we have HI going to H2 and I2, and we are given 8 molecules of H2 and 6 molecules of I2 to begin with. So now we're only going to have products. Okay, so in this one, we're going to actually do it all the way by ourselves. So we got ICE. Okay, so our initial values were, we had 0 for the 2HI. And then for H2, we had 8. And for I2, we had 6. Okay, so we know that we have no reactants at this point, so we're going to have to gain them. So we're going to gain, now we're going to have to throw these coefficients back in. Now we have 2x. And over here, we're going to lose, so it's going to be minus x and minus x because they don't have coefficients in front like the HI does. So on this side, we'll have 2x, and then we have 8 minus x and 6 minus x. So now we can go ahead and write our expression. So we have H2 and I2, and then on the bottom we have HI and it's squared because of that 2 in front. So now we can plug in. So we got 8 minus x and 6 minus x. And then HI was 2x, and we're going to square that. Okay, and that's equal to the k value, which, if you recall from the beginning, was 0.016. Okay, all right, so now it's just a matter of doing the math. So again, on this side, we have FOIL. So first, outside to inside, last. Okay, and on the bottom, we would have 4x squared. Again, cross multiply the bottom up. So 4 times 0.016 is going to give us all right, that's going to give us 0.064x squared equal to 48 minus 14x minus x squared. All right, now we need to get everything on the same side. Okay, so I'm going to go ahead and get this x squared over here. Okay, and screwed my sign up there. Man, where are y'all to catch my mistakes when I need them? So I'm going to minus this over here, and that's going to leave me with, let's see, what is it? 0.936x squared. Okay, so in terms of ABC form for the quadratic equation, we need to get it in x squared and then x and just our numeral there. Okay, and then we could plug this into our calculator. All right, so we're going to run our rate law program, not rate law, our quadratic formula equation again. And for A, we had 0.936. For B, we had -14. And for C, we had 48. Okay, and you see that that gives us 5.32 and 9.63. So let's go evaluate those numbers. All right, so when I go back up here to evaluate the x's, I got 5.32 or 9.63. Well, the 9.63 is not going to make sense because 8 minus that or 6 minus that is going to be negative, and we know concentrations can't be negative. So it's got to be the 5.32. So we do 2 times 5.32, we get the ending value for the first one. And then if we do 8 minus 5.32, we get 2.68. And then 6 minus 5.32, we get 0.68. So those are our ending concentrations for HI, H2, and I2. All right, let's look at another type, the last type. All right, the last type of equilibrium problem, you're going to be given some type of equilibrium information. So in this problem, we're given 2 moles of SO2, 1.5 moles of O2, and 3 moles of SO3 placed in a 1 liter flask. So 1 liter helps us because we know that we really don't have to worry about calculating concentration since everything's dealing with 1 liter. If it were different than 1 liter, we'd have to calculate the concentration, and it would be a little bit more difficult. And then we're told that we have 3.5 moles of SO3 at equilibrium. So let's go ahead and start making a ice chart for this one. Okay, so we started with 2 moles of SO2, 1.5 moles of O2, and 3 moles of SO3. Okay, let me go ahead and write these at the top. That way we remember what we are working with in each column. All right. Now, we're also told that we have 3.5 moles of SO3 at equilibrium. Okay, so that's our equilibrium value, so you need to put it in your E. Now, that means that when we went from 3 to 3.5, we added 2x, 2 because of this, right? All right, and that means that if we added this, we had to lose from the reactant side. So we had minus x and minus 2x over there. So that's 2 minus 2x and 1.5 minus x. And then over here, we know that 3 plus 2x is equal to 3.5. Okay, so that's going to allow us to determine the value for our x. So instead of doing the equilibrium expression here, we don't know k, so that's not really going to help us. We're going to have to find k. So instead, we're given different information. So we know that 0.5 is equal to 2x, which tells us that x is 0.25. So we're going to go back over here and we're going to apply that to all these. So 1.5 minus 0.25 is 1.25. And then 2 minus 2 times 0.25 would be 2 minus 0.5, which is 1.5. So these are all of our equilibrium concentrations for SO2, O2, and SO3. Now it wants us to calculate K. So we're going to have to write our equilibrium expression. So we're going to go ahead and throw that one down real quick. And then we're going to plug in our values to find the value of K for this reaction. Okay? All right, so this one's a little different because you don't need the quadratic formula to solve it. And I got 4.36 as my K. Okay, so those are the 3 types of equilibrium problems that you may run into and how to solve them.